There we go. Okay, that should go now. It takes about 20 seconds, to spool the buffer, because we are looking at a combined, spooling. Okay, it should be up now. And let me check the audio on the other side. It should be okay. It takes about, yep, okay. All right, so now we can get started with floating point number representation. So instead of getting into the actual floating point number representation, right away, so what I'll do is I'm going to first introduce scientific notation. Okay, so hopefully everybody in this class already know what is scientific notation. If not, this is a very quick introduction to scientific notation. Okay, so let's say that we want to express a really big value or really small value. Okay, let's start with a really big value. Okay, let's just pick the speed of light. Okay, speed of light, and it is 299,792,458 meters per second. Okay, so this is just accurate down to the meter. I think, in terms of in the units of meter per second, pretty sure this is going to be an irrational number, but we'll just take this. Okay, so what we'll do is instead of using all of these digits, so if I only care about like one or two digits of significance. In other words, I look at it and go like, it looks close enough to 300 million. Okay, then what we'll do, okay, getting back to the whiteboard, is I will express it like this. Okay, so I'm going to express it like it is 3 times 10 to the power of, okay, so let's do some counting over here. So we have, I believe it is 8. Okay, okay. So this value here, 3 times 10 to the power of 8, is expressing a value that is kind of close to the speed of light. Okay, it's off by a little bit, but for most practical purposes, it is close enough. So does everybody understand, this, why this representation is pretty close to, the actual the speed of light down to meter per second? Okay, so if we don't have a question about that, then we'll go ahead and we'll express the same thing, but this time in scientific notation. Okay, so when we express this in scientific notation, then it is known as 3e 10 and 3e8. Okay, as a scientific notation. So in this case, 3e8 means 3 is known as quote unquote the Mantissa. So we'll talk about why Mantissa as a term is kind of it's there's a lot of misunderstanding of what Mantissa is, but we'll look at the 3 as the Mantissa. Okay, so 3 is the Mantissa, and then 8 is the exponent of 10. In other words, instead of writing the whole thing out as 3 times 10 to the power of 8, we have a shorter notation of using 3e8. And by the way, this is the notation that C and C++ use to express values as a float or as a double. So do we have any questions about the shorthand of expressing 3 times 10 to the power of 8 as 3e8? Okay, all right. So I don't want anyone to tell me that this is 3 times e as in the constant of natural log times 8, because that is not what it is. Okay, because I'm every year, when people are doing the lab, someone is bound to look at 3e8 because they copy and paste it into a calculator, which will then interpret it as 3 times the constant of natural log times 8. Okay, that is not the case. Okay, 3e8 means 3 times 10 to the power of 8. So this is scientific notation in base 10. Are we doing okay so far at this point? Or do we need any clarification of scientific notation in base 10? Okay, I'm not seeing any questions in the text channel, so I will then proceed to talk about base 2 values. But before we move on to base 2 values, then we'll go ahead and look at something that is not an integer. Okay, so because the whole point is we want to be able to express a non-integer value. So this is something that we have seen already. Okay, if you remember in base conversion, we have already dealt with values that are not integers, and we have already learned how to express those values in base 2. But in those particular values, we have the decimal point, or to be more precise, the binary point, because we're dealing with binary numbers and not decimal numbers. So we still need a point notation in order to separate the digit corresponding to 2 to the power of 0 versus 2 to the power of -1. So let us just kind of review that first, okay? So we'll go ahead and say, consider the value of, let's make it 61.375, okay? And that's a base 10 number. So what we want to do is to say, okay, how to express the value of this base 10 number in base 2. Okay, so this should be something that you know how to answer already. And by the way, there will be questions. Well, okay, there will be questions covering the same scope in exam 1. So if you have not studied how to do base conversion, well, guess what? This is a review that might be helpful. Okay, so the idea of a base 2 number is we are expressing the value, which is to us known as 61.375 as a base 10 number. We want to express it using just zeros and ones as a base 2 number. But each digit of the base 2 number is expressing the quantity of a particular power of 2. So now we want to look at 61.375 and ask, how do we break this up into powers of 2? So let's go ahead and take a look at that. Okay, so we will say, okay, so we're not gonna deal with powers of 2 that are greater than 61.375. So 64, which is a power of 2, is not going to be considered here. So we'll get down to 32. So now we want to say, how many of 32s do we have here? The answer is, well, we got one of them, right? Okay, so we change the question mark to a 1. And then now we ask, after that, do we have any 16s? And the answer is, yep, because after we take care of the 32, we have, 29 left, which means we do have a 16 after that. So we do have a 16. So after the 16, we ask, how many 8s do we have? So now we say, well, it's 61 point something. After we get rid of 48, it would be, what, 13 point something? So in 13, that we definitely have an 8. Okay, so there's one 8. All right, so now we have taken care of 56. So after we have taken care of 56, the next question is, do we have any 4s? Okay, and the answer is, yeah, there's a 4. Okay. And now we have taken care of a quantity of 60. But the question that we're going to ask next is, do we have any 2s in it? Well, let's see. If we have taken care of 60 out of 61 point something, we only got 1.375 left. So we do not have a 2 in it. So the quantity of 2 is going to be a 0. And we still have 1.375 left. So now we ask, how many 1s do we have in 1.375? Well, that is a pretty easy question to answer. We got 1 of 1 in 1.375. So now that we have taken care of the integer part of 61.375, we have 0.375 left. But the next power of 2 that we have to deal with is 0.5, which is 1 divided by 2. So we ask, how many 0.5s do we have in 0.375? The answer is none. Now we move down to the next power of 2, which is 2 to the power of -2, which is known to us as 1/4. or 1/4, or 0.25. So now we ask, how many 0.25s do we have? And the answer is we got one of those. And then we move down to 0.125. So at this point, the value only has 0.125 left, and we're asking how many 0.25s, how many 0.125s do we have, which is an eighth. So the answer is we got one of them. Okay. So this is the first step of base conversion, which is basically expressing a particular value as a sum of powers of whatever base we want to convert to. So now we take this and we ask, okay, so we look at this and say, can we convert every single one of these into an actual power of 2? Well, that's not too hard. This is 2 to the power of 5. And this one here is 2 to the power of 4. I mean, you guys get the idea, right? This is 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of 0, and then we go negative, right? Because the 0.5 is nothing more than just 2 to the power of -1. And then here we have 2 to the power of -2. And here we have 2 to the power of -3. Okay, all right. So once we have the number, expressed like this, then we can now break it down and say, oh, okay, so this is 1 followed by 5 zeros, 1, 2, 3, 4, 5 in base 2, which is basically the base 2 version of 2 to the power of 5, plus 1 with 4 zeros after that, which is representing 2 to the power of 4, 1, 2, 3, 4, and 1 of 2 to the power of 3, so we have 1, 2, 3 zeros, and we have 1 of 1, 0, 0, and we don't have a 1, 0, but we have a 1. And then guess what? The other side are the these are the decimal places, or these are the digits to the right hand side of the point. So we have none of 0.1, okay, because this is 0.1 and this is 0.01, because where the 1 is to the right hand side of the point indicates how negative that power of 2 is. So we have 0.01 in base 2, and then we have 0.001 in base 2. So are we doing okay so far with this notation? Because this really, I mean, from this row to the row that I just worked on, that really is the core of base conversion. Okay, so I just want to make this more clear as to what we are dealing with. So we have 61.375, which is a base 10 number. Now it is expressed as a sum of powers of 2, except each power of 2 is now expressed in binary instead of in base 10. So do we have any questions at this point about this base conversion? Okay, I don't see any questions. All right, so without any questions then we'll say, oh, okay, so a more handy way, a more concise way to write this is simply to say this is 1, 1, 1, 1, 0, 1 in base 2, 0.011 in base 2, because this is basically, this number here is basically just a summation of all of these base 2 numbers. So Duck is asking, is this lecture in the exam? That's part of what I just said. The conversion up to here is part of base conversion, which is in the exam. So we have not even gotten to the part where we are dealing with floating point numbers yet. So the answer is yes, part of today's lecture is within the scope of the exam. When we get to the floating point part, then it is not in the scope, because base conversion is in the scope, and so far what we have done is just base conversion. All right, So that's a good point, because now we can say, we look at this and go like, hey, we can express it in a slightly different way. We can actually move the decimal point a little bit. Okay, so what I'm going to do now is to say 111101.011 in base 2 is, I'll just move the binary point to the left just once. Okay, so we'll end up with 1111 0.1011. Okay, let me just double check to make sure I did it correctly. All right, so this equality doesn't make sense, right? Because when we shift the binary point, that would have changed the value that the number is representing. So now the question is, how is the value represented by this number relate to this number in base 2? We know this equality doesn't hold. Okay, we already know this doesn't hold, so we're going to fix that later. Okay, but right now we are concerned about what value is this representing and what value is this representing. How are they related? So does anyone want to kind of contribute to figure out how those two values relate? Because if nobody is going to volunteer any information, then I'll try to explain this in the most boring way possible. A factor of 2. All right. Okay. A factor of 2, which one is twice of the other one? In other words, okay, exactly. So the times 2 go on to this side. Okay, so let me type that here. Okay, so that's a times 2. Okay, we're just using asterisk to mean multiplication. And this 2 is in base 10, okay, because you do not have a digit of 2 in base 2, okay? All right. Does everybody understand this part, okay? Why we have this equality where, if we shift the binary point to the left by 1, then we have to make up for the magnitude by multiplying, the value of whatever is left times 2. Okay? Okay, all right. So if anyone is having a problem understanding this, it's okay. Okay, it is not a problem. So for those people who have a question about this and it's really kind of asking why is 111101.011 base 2, why is that the same as 11110.1011 in base 2 times 2, then I will ask those people this question. Okay, so I would say that to convert 1111 0.1011 in base 2 to base 10. Okay, figure out what that is, because what you should see would be 1/2 of 61.375. Okay, this value here in base 2, if you convert it back into base 10, should be 61.375 divided by 2. All right, so Aiden types, you could even say it is times, yep, because 1 0 in base 2 is 2. But there's a reason why I choose this 2 over here, which will be clear in just a little bit. All right, so this is this question, okay, for people who cannot see the equality on the previous line. Okay. All right, so this is an activity for those people who kind of need to do something by hand and look at a concrete example to understand. Okay, so what I'll do next is I'm going to move that point to the left one more time. Okay, so I'm going to say 111101.011 in base 2. And now I say, let's move that binary point one more time to the left. So we end up with 1111.01011 in base 2. Obviously, this equality doesn't hold. So now the question is, how does the number to the left relate to the number to the right? So I think most of you are kind of getting an idea right now. So can someone tell me what I need to do to one side? Okay, let me make to be more specific. What can I do to the right hand side of the equality In other words, what can I do on this side so that the equality holds? Yep, factor of 4 times 2 times 2, okay, they all work. So we'll go ahead and say that, except I'm going to say it's 2 to the power of 2, okay? And since I'm using this notation, might as well turn on the LaTeX representation, okay? And we'll turn this into a C dot. So it's kind of more of a convention in mathematics. Of course, I can use the subscript of 2 instead of parentheses 2, but it's too late to change that. So are we still doing okay with this? So you can see every time we move the binary point to the left, we have to multiply the value by 2 if we want it to represent, if we want the expression to express the same value, if we want to preserve the value. So using this method, now I can say, let's move that point 3 more times, okay, to the left. So now we have 11101.011, which is the original value, being equaling to 1.11101.011 in base 2, okay? But obviously we need to multiply, this with a power of 2 to make up for the magnitude of change. So now the question is, how much do I need to multiply this? In other words, what would be the power of 2 that I need to multiply on this side so that we still have an equality? 5, all right. So I kind of feel like, I'm one of the characters in Sesame Street, right? Because, hey, if we move the binary point once to the left, we have to increase the power of 2 to compensate for the value by 1, right? So I have to move the binary point 3 more times to get to here. So that means whatever the power of 2 is here, which is 2 itself, needs to increase by 3. So now we end up with 2 to the power of 5. So are we still doing okay so far? All right, very good. Okay, so Quan, Daniel, and Alex, all those answers are correct. Indeed. Okay. See, computer science is no more difficult than topics in Sesame Street. Okay, I'm not getting any response, because people do not watch Sesame Street anymore. I used to be afraid of the count, by the way. No, I think the kids would be rejoicing. Okay, base 2 is the best base, man. You forget about base 10. All right. So now we look at this and go like, what does this have anything to do with floating points? Okay. In other words, hey, okay, we can see how this number as a base 2 number is the same as this number here, which is also a base 2 number, but it has a magnitude which is expressed as 2 to the power of 5. Well, don't you think this has some resemblance to the scientific notation, where we specify a certain value, okay, and then we specify a power of the base that we are using in order to express the value that we want to express? Hey, it's the same idea. Okay, this is really the same idea. So this is where I break off what would be in the test. Well, actually, I should say where I will break off what will be in the test and not in the test is about here. This is the last portion about base conversion. Okay, let me just move back by one row. This is the last portion that is still related to exam 1, and everything after that are new topics. Okay, so but in terms of concept, okay, it's really a continuation, a very natural continuation of of this line over here. So now we look at this and go like, hey, this is a scientific notation, except it's in base 2. And that's basically what a floating point number is. Okay, a floating point number is a scientific notation number, a scientific notation but in base 2 instead of base 10. That's basically what it is. All right. So now we have to refer to specific terms, in here. Okay. So we'll look at the example that we have. Okay. So, and I'm going to be more specific, and we'll say in this example, okay, 1.111.01011 in base 2 is the mantissa. In other words, the mantissa, okay, in a very loose way of using that term, is referring to the coefficient, okay? What is the quantity of, in this case, a power of 2, okay? So this is the quantity that we are talking about. And then we will say, 5 is the power of 2 to multiply to the mantissa to get the value being represented. Okay, so, but we're going to give that 5 a specific name. Okay, so I will give it a name of E2. So that's basically just how we define E2. So E2 is simply defined to be the power of 2 that we want to multiply to the mantissa to get to the value that we want to represent. Is that okay? Does everybody understand what E2 is doing? Okay. And I will even give this portion a name. We'll just call it M. Okay, M for mantissa. See, Sesame Street. Okay, we are learning the letters and we are learning the numbers. So M is the mantissa, E2 is the power of 2 that we multiply to the mantissa in order to get to the value, which is V. Okay, so you will see these notations in the notes. Okay, so that's why I'm putting it here as well. So in this case, V, which is the value being represented, is the value being represented in by 61.375 in base 10. Okay. So we got M, which is the mantissa. We got E2, which is the power of 2 that we want to multiply to the mantissa. And when you have that product is called V, which is the value being represented. Are we doing okay so far? Okay. All right. Okay, which part is confusing? Are we talking about which part is the mantissa, or are we talking about how the conversion happened? How do we move the binary point to the left and end up with a power of 2 to make up for the shifting of the binary point? How do we notate it scientifically in base 2? Well, this is it. This is the best we can do, is just that, okay? So we express the mantissa as a coefficient, and then we express the power of 2. Well, in this case, in base 10, because instead of writing 1 followed by 5 zeros in base 2, it really is the same thing as just what we know as 2 to the power of 5. So that is, why can't we use E? Because then it will be confusing, because the E notation is pretty much reserved for base 10 scientific notation. So when we have a base 2 scientific notation, I just make it very explicit and not use the E notation. So are we still okay, or more things for me to clarify? Are there more items for me to clarify? Okay, so no scientific notation in base 2. We simply deal with big numbers. It's just that we express it like this instead of using an E here. So there's no shorthand. Okay, there's just no shorthand to do it in base 2. In base 10, we have a shorthand just because C and C++ would use this shorthand. Okay, so this is also a time to warn people and say, you have to find out how your calculator expresses scientific notation because every calculator is a little bit different. On a Casio calculator, there really is a small E button. No, I take it back. I think it's EXP button that expresses, which portion is the power of 10. If you type this in the C program, then the E is sufficient to separate the Mantissa from the power of 10, which is 8 in this case. So, when you do the homework assignment or the lab tonight, you kind of have to learn how to use your calculator correctly. Because if you don't, okay, a lot of times E is also known as the natural log, okay? So when you say E3, E8 on the calculator, it is very possible that it will do 3 times E to the power of 8 instead of 3 times 10 to the power of 8. So you gotta make sure that you know how to use a calculator if you plan to use a calculator for today's lab. All right, so are we good so far, or do we need more time to digest this, or are there more specific questions? Because you guys can always refer to a particular item and just say, I'm not quite sure what that means or how we got there, how it relates to the previous line. Okay. No questions. All right. So with all of these topics done, we can now talk about the IEEE double precision floating point number format. That is a really long phrase, okay? So from here on, we'll just call it double. And this is also a good time to mention tonight's password for row taking. So for row taking, the word is, it's not even a word, it is an abbreviation. It is IEEE, all lowercase. Yep, I. No, without the S. Don't, Tom, try not to confuse the rest of the class. It's just IEEE, which is the name of the institution. No, double is the passcode of the lab. So Aiden, you're pretty close at emulating how I think. Yep. So pretty good guess. Just so double is the passcode of the lab itself, and then IEEE is the word for row taking purposes. Very good. All right. So for that portion, I'm going back to my notes. Okay. And my notes is going to Wikipedia. Yes, I know a lot of professors choose not to use Wikipedia, but I look at it and go like, hey, it's free. I don't have to redo things that are done already, so why not? All right. So the double precision floating point number format, okay, has a picture. Okay, so let me scroll to the picture part. Hey, this is the picture part. So every little cell within this picture is 1 bit. And they even number bit 0 all the way up to bit 63. So what this is telling you is an IEEE double precision floating point number takes up 64 bits or 8 bytes, okay? So it is broken down into 3 distinct portions, which are color-coded here. I'll talk about the easy part first. The easiest part is bit 63, which is known as the sign bit. Now, when we are talking about the sign bit of a double, it has an entirely different meaning. Well, I shouldn't say entirely, but it has a very different meaning compared to the sign bit of an integer. Okay, so just kind of keep that in mind. We'll get to it. The next, let me see, the next 11 bits are known as the exponent, but it's not what you think it is. So right now, instead of looking at these 11 bits, which are color-coded green, we'll call that the biased exponent. Okay, we'll talk about this in just a little bit. So when you see exponent here, just insert the word biased. Okay, it is a biased exponent. And then when we see the pink or salmon yellow color portion, which is known as the fraction, just remember this is the fraction of the mantissa, okay? Because these words are they can be confusing by themselves, okay? All right. So given these 64 bits chopped up in this particular fashion, what is the value represented? Well, you can use either this expression or this expression here to find out what the value is. You look at each one, okay? Let me zoom in so it's easier for me to point to individual items. So when you look at each one, it's like, whoa, that's really kind of difficult to read. Well, okay, let me just read it out loud first, okay? This really is -1 to the power of sine. But sine is only 1 bit, which means the value is either a 0 or 1. So when sine is a 0, -1 to the power of 0 is 1. When sine is 1, then -1 to the power of 1 is -1. So when you only focus on this portion here, then it will just give the sign of the value that is expressed by the rest of the bits. In other words, the sign bit in this case truly is only indicating whether the rest of the value is negative or non-negative. Okay, it is not the presence or the absence of a large power of 2, which is how we interpret the sign bit in a signed integer. Okay, so now we move on to the rest. So in one form, it says 1 point, B 51, 50, 50, blah, 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 all the down to 0. So what this means is you take these 51 zeros and ones and paste it to the right-hand side of the point. That would be the mantissa, okay? In other words, the 1 point is always there, okay? This 1, which is to the left of the binary point, is always there. It is not explicitly represented as one of the 64 bits of a double, okay? And then the power of 2 that we multiply to the mantissa, because this entire thing is the mantissa, and that's why bit 51 down to bit 0 is known as the fraction, because it is the fractional part of the mantissa. But the exponent, the exponent of 2 that we multiply to the mantissa is not just e itself. And by the way, this e would be the unsigned value represented by these 11 bits, okay? So those 11 bits, the unsigned value of these 11 bits is known as e in this case. But the actual power of 2 that we multiply to the mantissa is e minus 1023. So 1023 is the bias of the biased exponent, okay? Are we still doing okay so far with this explanation? Okay, to Daniel's question, I'm going to ask what? And then to that question, I will ask, what do you not know? You can see how quickly I can go around in a circle. Endless recursion, stack overflow, dead. Okay. So E is a biased, okay? It's a biased exponent. So if you want the exponent of 2 to be actually 0, then you want E to be 1023, which means you have basically 10 ones over here and a 0 leading the 10 ones. I think it is best to give you guys an example, right? Let's work with an example. I think that will clear up everything. Yep. And recursion is not scary. Recursion is your best friend. And by the end of this semester, we'll be writing recursive subroutine calls in assembly language on an architecture that is simulated in Logisim. So stuff that you can look forward to. Yay! All right, so let's go ahead and take a look at it. Let's take a look at an example, okay? So we have an example, and we'll have 1, and then we specify, let's see, 1, and then a bunch of zeros, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and then we express some numbers over here. We'll just put 0, 1, 1 down here, and then we just have a whole bunch of zeros in base 2. Okay, so these are the actual bits of a IEEE double precision floating point number. Okay, so inside the computer, these are the zeros and ones of a specific double. So now we want to look at this and go like, okay, Jack, you can just throw a whole bunch of zeros and ones, but what is it representing? Okay, so I'm going to work on this step by step, okay, so that we can actually find out what it is representing. So the first thing I need to do is to turn it into a pre-formatted thing, okay, so this way I can actually label each individual bit. This is the sign bit, okay, the leftmost one, or the most significant bit, is the sign bit, okay. If it's a 1, then the quantity is negative. If it is a 0, then the quantity is non-negative. That's the only way to interpret that one. These guys, okay, I'll put E's down here. So they're basically what we know as E in Wikipedia, the biased exponent. These guys are labeled F's because they are the fraction of the Mantissa. Okay, so are we doing okay so far, of how to chop the individual bits, or how to chop up the 64 bits into the 3 portions that we have seen in Wikipedia? This leftmost one is the sign bit. The ones labeled E is the biased exponent, and then the ones labeled F's are the fraction of the Mantissa in base 2. Cool. All right. Thank you for the confirmation. So now we move on. So now we say sign is a 1, so the value is negative. That's all it is saying. Okay, the sign bit is really just saying is the value negative or not. In this case, it is. So now we say E equals to 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 in base 2. Okay, but it's biased. Okay, but we still want to find out what it is, right? So let's go ahead and find out what is the base 10 representation of 1 followed by a whole bunch of zeros and then 1, 1 in base 2. So the difficult one is what is this one representing, okay? But we can count, right? Because there are 10 digits here. So there are 10 digits down here. So that means whatever this one is, it is representing the quantity of 1024, which is 2 to the power of 10. So now we can say, oh, okay, so we now know how to read this thing. It is 1024 plus what this particular one is representing, and that's representing a 2. And this one over here, the least significant bit, is representing just the number of ones. So now we add up all of these things, we end up with 1027 in base 10. So Daniel is correct. Okay, he's actually faster than I am. Cool. So are we good so far of how we evaluate E? It's just looking at all those bits as an 11-bit unsigned number, okay? All right? But the actual exponent of 2 is, because E itself is biased, right? So E2, which is the actual exponent of 2 that we want to multiply to the Mantissa, is 1023 minus 1023. Excuse me, 1027 minus 1023, because that's what the rule says, okay? Don't ask me why it is 1023 and not 1024, because IEEE decided 1023 is the bias, okay? That's all there is to it, okay? So is this part okay? How we got to E2? I just said, don't ask me, Daniel. All right, cool. Yeah, I'm not gonna say anything because if they had chosen 1024, everything would even make a lot more sense, because in that case it just becomes the They could have chosen the signed representation of an 11-bit number, but they decided not to. Yeah, that's what happens when you have electrical engineers doing the job of a computer scientist. Yeah, they would like to think that they are computer scientists as well, but guess what? They're not. Yep. All right. So now we move on to the fractions. Okay, how do we look at all the bits that are labeled F? Okay, all the way down here. So now we say, okay, so the only part that is missing is the mantissa. So now we say, what exactly is the mantissa? Well, as it turns out, the 1 point is always there. Okay, this 1 point is not represented as a part of the 64 bits. Okay, uh, it's just a fixture in the room. Okay, it's always there, but the other bits are not. So now what we do is we will copy all of these bits over here to the right hand side of the point. Okay, so I can do that, or I can just type it out. So we got 0, 1, 1, and then a whole bunch of zeros, blah, 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 all the way, So how many zeros we append to the right hand side really doesn't matter because they're all zeros. So it really is not contributing to the mantissa. So are we still doing okay? Does everybody now understand why I call, let me point out, why I call these bits the fractional side of the mantissa? That's why is there a 1 in front? Because that is how we do not represent the 1 point. So the 1 point is always there. Because we save 1 bit. Because, okay, so let me explain that. Okay, that's actually an interesting question. Because when you look at the mantissa of a base 10 number, now when we talk about mantissa, the mantissa part should not be a value that is greater than the base itself. So in base 10, the mantissa can go from 0 all the way up to 9.9999999 something. Okay, all right, so that's the first thing we want to know. Okay, but because this is a base 2 number, right? So in a base 2 number, the mantissa can go from 0 to 1.1111111 in base 2. It cannot get up to 2. Okay, but there's no way we can change this 1 to anything other than a 1. It cannot be a 0. Actually, I take it back. The mantissa has to be at least 1, but always less than the base that we are dealing with. So in base 2, this digit in a mantissa is locked to a value of 1. Okay, Daniel is typing, so I'm base 0.5, which is base, so base 0.5 would work, you just have all the exponents flipped. I think Aiden actually suggested this when we were talking about base conversion. So maybe that would be a conversation with Aiden offline, okay, not during the class. So anyway, the question I have to the whole class is, does everybody now understand why this portion, which is also this portion here, is known as the fraction of the mantissa? Because this entire thing is the mantissa, but the 1 point portion is not represented explicitly because there's no other digit, there's no digit other than 1 that can go here. And if it has to be a 1, then why do I want to waste 1 bit to represent it? Yeah, base -2 doesn't work because you cannot represent all the values. Yeah, you cannot represent all the values because even powers and the odd powers, they cannot make up all the values that we need to represent. So it wouldn't be continuous, as integers. Enough distraction. So are we doing okay so far with what the sign is doing? What E is, okay? E really is just the unsigned interpretation of these bits. And what E2 is, which is the value of E minus the bias, which is 1023. And M is basically 1 point, and then we just copy all the bits of the fractional part of the mantissa after the binary point, and that would be our mantissa. Cool. So now can we get to V, right? When are we going to get to the value being represented here? Well, we got all of these components. So we know V is always M, which is the mantissa, times, okay, I'm just going to use C dot here. It will look right after I'm done typing the whole thing. So it's M times 2 to the power of E2. Okay, so now everything looks right. Okay, so it is M, which is our mantissa, this guy here, times 2 to the power of E2, which in this case is 4. Okay, so let me just kind of make sure that this is 4 over here. No. All right. But can we get to the value? Okay, so we want to figure out the actual value. Then I'll show you guys how to do this as an experiment. So how do we call the xxxx? That's the fractional part of the mantissa. Which is labeled f in the map here, which is also labeled f, or fraction, in this picture. So are we okay, with how we call these various parts? Okay, all right, cool. Well, this is why we work out an actual example, because now we work with actual bits, and actual values. So now we look at this and go like, what exactly is M? Well, we'll do the conversion on the fly this time. So it's 1 because of the 1 to the left-hand side of the point. Then we do not have any halves. We do have 1/4 because this one over here is representing that we have 1 of 2 to the power of -2. And this one over here is telling us that we have 1 of 2 to the power of -3. So when we have 1/4 and then we have 1/8. Okay, that together is M. Then we have times. We already know what is the value of E2, which is 4. So we have 2 to the power of 4. That is V. Okay, and I need parentheses. So let me put parentheses around all of the components of the mantissa. Okay, so we look at this and go like, okay, so let's work this out. Okay, because now we have 1.375 times 2 to the power of 4, and no, it cannot be that big. It cannot possibly be that big, because 2 to the power of 4 is 16. So at the worst we can get 31. Okay, we can close to 32, but it's not even that. Okay, so now we have so there are other ways to look at this. Okay, this is 1 3/8. So 1 3/8 is what? So let me look at this from the fraction perspective. So we have 1 3/8, which is 11 divided by 8. And then we want to multiply this whole thing by 16. Okay. So now we just work this out. The 2 and the 16 would mostly cancel out with the 2 on top. So we have 22. There we go. So that means if you give me a bit pattern, a 64-bit bit pattern, starting with this 1, and then another 1, a bunch of zeros, and then 1 1, and then a 0, and then 1 1, and then a whole bunch of zeros after that. And if I choose to interpret these 64 bits as a IEEE double precision floating point number, they together, the 64 bits together, would actually be representing -22, because we have to factor in that the sign bit is a 1. Okay, yep, very good, Daniel. You got it. Okay, so I have just mentioned a whole bunch of mumbo jumbo, gave you guys a whole bunch of zeros and ones, and claim that it is representing -22. Okay, obviously you are not going to buy that. Okay, Because if you're going to buy that, then I would be very concerned about your vote this November. Right? Okay. So you guys would say, but Tech, we're not going to buy this. Okay. You have to show us, that, this actually works out. Okay. So I'm going to show you how this is all going to work out. Let me see how I would do that. And I think I got a way to do it. Let's see. All right. So this is how I would do it. Let me zoom in just a little bit, but I do want to preserve, portions of the whiteboard. Okay. So I am going to give you a magical program that will help me figure out all this stuff. Okay. So let's go ahead and work on the magical program. I'll call it test.c. Okay. Nope, it's not LogicSim. This time it's really a C program. Okay. And we'll say pound include stdint.h, standard integer.h. So the nice thing about standard integer.h is now you can refer to types of integers by their width. Okay, so you can basically lock down that I want a 64-bit integer, because if you just say I want an integer, depending on the compiler and also on the platform that you're running the compiler, it can be a 16-bit integer, can be a 32-bit integer, can also be a 64-bit integer if you just say int. But in this case, we have complete control over that, because now I can say uint, which is unsigned integer, underscore, and then 64. This is the name of uint64 underscore. Oh, okay, I take it back. uint64 underscore t. There we go. So this is a type def, okay, of a 64-bit unsigned integer. Regardless of the platform, regardless of the compiler, if you pound include stdint, which is standard integer.h, then this particular type uint64 underscore t is always going to specify a 64-bit unsigned integer. So this is really useful because this is how you can write code that will work across platforms. Because now if you compile it with a 32-bit compiler, it will still say that x is a 64-bit number. Okay, so let's finish this magical program. So we'll say x equals to, give it a 0, return 0, and here it is. This is the entire program that I need to verify that this kind of insane bit pattern is really just representing -22. All right, so we'll get out of the editor and get it compiled. So we have gcc-g to include debug information, -o to specify the name of the executable, and then test.c to specify the source of the file, the source code, and press the enter key. No syntax error. Okay, so everything is good. So now we use GDB, which is GNU debugger, to debug the test program. Cool. And we list the program using L, and then we put a breakpoint on line, we'll put it on line 8, sure. There we go. And then we run the program. We print x, and x has a value of 0. We go like, okay, that's good, very good. But what does it have anything to do with what we want to do? Because remember, what we want to do is to say this particular bit pattern, which is a 64-bit, is really representing the value of -22. That was what we wanted to do. This program doesn't seem to have anything to do with it. And if you have been thinking about that, you would have been right. This program really has nothing to do with that. But it gives us the tool so that we can actually do what we need to do. So the next thing we need to do is to enter this entire bit pattern into X, okay? Not -22, but this entire bit pattern. Normally in C and C++, there's no base 2 representation, but since we're in GDB, there really is a base 2 representation. So you can say set var x equals to 0t. That's the prefix of specifying a base 2 number. Then we can specify 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 0, 1, 1, and then whatever the number of zeros we need down here. That's a lot of zeros, okay? And I hate typing all the zeros. So this, even though it's doable in GDB, it's not really the best way to do it. Okay, so if that doesn't work, how are we going to do? This is where I'm going to introduce base 16. Okay, so don't worry about conversion of base 16. It is not going to be in exam 1. But I do want to show you how to convert a bit pattern from base 2 to base 16 because it's actually quite useful that you learn how to do that. So what I'll do is I'm going to go back here, okay, copy this line down here, and now we'll go ahead and kind of rearrange the spaces a little bit. So instead of looking at this entire thing as one contiguous, bits, we'll chop them up into chunks of 4. Okay, there we go. And the reason why I break it up into chunks of 4, and the reason why it is 4, has to do with how 2 and 16 are related. So can someone tell me how 2, 16, and 4 are related? Daniel is typing, so I'm waiting a little bit. And so is Alex. All right. No, we are not concerned about base 10. We are only concerned about base 16 because the conversion from base 2 to base 16 is easy. And that has to do with the original question that I posed to the whole class. How are these values related? 2, 16, and 4. Okay, that's all right. The answer to that question is 2 to the power of 4 is 16, which is basically saying that it will take 4 bits to represent 1 digit in base 16. That's it. That's why I chop it up in chunks of 4. So now that it is expressed in chunks of 4, I look at 1100. It is represented in hexadecimal as C, which is what we know as 12 in base 10. 0000 is just 0. 0011 is 3. 0110 is 6. And then we have a whole bunch of zeros after this. Yep, Darwood is correct. So now the rest are all zeros. How many zeros are we talking about? So we got 4 non-zero hexadecimal digits. So how many more zeros do we need to make up 64 bits? Each hexadecimal digit is specifying 4 bits. So C036 will take care of 16 bits right there. But we need 64 bits. So we have 48 bits left to specify as zeros. But each 0 in hexadecimal is going to specify 4 zeros in binary. So now the question is, how many zeros do we need? 12, very good. So we have just moved a little bit beyond Sesame Street because there's division now. Yay, cool, right? Forget about politicians. Okay, they are not the divider. I am the great divider because I can divide 48 by 4 and get to 12. Cool. All right. So the question is, what does this have anything to do with the debugger? Well, now we have a very convenient way to express those 64 bits so that we can initialize x to those 64 bits. So we'll do it this way. We'll say set var x equals to 0x, which is the prefix to specify a base 16 number. Now 0t doesn't work in a C or C++ program because it is just not a part of the C language. But 0x as a prefix of a base 16 number does work in C and C++. So now we specify 0x, and then I'm just going to copy the rest, which is C036, and then 12 zeros. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Back to Sesame Street. Back to the count, right? Cool. Press the enter key. Okay. And nothing happens, right? So we say, okay, tell me what is x. Okay, if you're expecting x to be negative 22, you cannot be more disappointed because it's not even close to that, right? It's not even close to the bit pattern that we want to specify. Or is it? In GDB, you can specify that you want to print a value in binary. Okay, so print /t means I now want to print something in base 2. Okay, Christy says, why did you write C? C has to do with 1100 is specifying what we know as 12 in base 10, but in hexadecimal, you use single digits to represent everything up to what we know as 15. So after we count to 9, then we start to borrow letters from the alphabet. So we have A representing 10, B representing 11. So by the time we get to 12, which is what 1100 is, we'll get to C. Okay, so that part I didn't quite explain because I wasn't too concerned about the mechanism of base conversion at this point. Okay, you're welcome. So now we say print, press the enter key, and go like, okay, what are we having here? Hey, that looks familiar. We got 1100. Okay, 1100. We got 6 zeros after that, right? So getting to this part, we got 6 zeros after that, and then we got the 1 1, and we got the 0 1 1 0, and then a whole bunch of zeros after that. Okay, but where's my negative 22? Somebody's going to say, oh, we need typecasting, okay? And you are correct about typecasting. Is the problem with you declaring as an int and not as a double? That is correct. In other words, when GDB is saying, when I ask GDB to show me the value of x, GDB is looking at the type of x, which is an unsigned 64-bit integer. So GDB is basically saying, oh, okay, if you don't specify the base, I'll give you the base 10 version of that value. But GDB is looking at the 64 bits as an unsigned 64-bit integer, and this value is actually correct if you want to look at those 64 bits as an unsigned 64-bit integer. But that's not what we want to do. We want to find out, if we choose to interpret those 64 bits as a double precision floating point number, what value would that double be representing? So people go like, oh, we just need to typecast it, right? So print double x, okay? Well, unfortunately, this is not going to work. This will give us something close to what we had, but not exactly. Okay, what is going on here? Yep, so Aiden is right, okay? So let's go ahead and explore what Aiden, well, instead of copy and pasting Aiden's solution, let's go ahead and look at that thing one step at a time, okay? We first start with x, okay? What is the type of x? It's a 64-bit unsigned integer, right? Okay. So we now say, what is this, okay? What is ampersand x? It would be the address of a 64-bit unsigned integer. Go like, okay, well, that's not getting us anywhere. The unsigned integer part is still here. But we do have an address here. Whenever you have an address, you can do a typecast on the address itself, okay? So now we say double, okay? Oops, double star, okay? So what is this doing, okay? So we have to read from right to left, okay, which is kind of awkward when we do programming in C and C++. So x is an unsigned 64-bit integer. Ampersand x is the address of a 64-bit unsigned integer. But now that we have an address of something, we can say, well, let's not look at this as the address of an unsigned integer, unsigned 64-bit integer. Let's look at this as the address of a double. Okay. In other words, it is the same location. It has exactly the same content, but you choose to look at it differently. Okay? Well, now that we have the address of a double, we can say, let's dereference it. Okay? So this expression as a whole is basically um, letting us to choose to interpret the 64 bits that was in the C program seen as a 64-bit unsigned integer, but now we say, nah, we choose to look at it as we choose to look at the address as the address of a 64-bit double, and we want to dereference. Okay. In other words, now we want to say, what is the content of this location? And we know this location is a double because I casted the address first to the address of a double. So now we look at the answer and go like, oh, that is good, right? It's good and bad in a way because um, if you look at all of this stuff here, and think that this is weird and you're not fully getting everything, that's okay because you can rewatch this video, but slowly this time. Okay, so you gotta make sure that you make association between all of the steps. But if you look at this and go like, yep, that's kind of what we expect because the math all works out in my head, then congratulations. Okay, we have just concluded an experiment to explain what IEEE double precision floating point numbers are all about. So do we have any questions at this point? Because we got 7 more minutes before we run out of time for this lecture, because if there are no questions, I can always move on to the next portion of this module. But if anyone has any questions, then we'll go ahead and address those questions. No questions. How about this? Let's reverse this process, okay? In other words, we go back to the example that we had earlier, which is 61.375, and then we want to find out what is the representation in zeros and ones. Does that sound good to you? I think that's a good use of the last 6 minutes of today's lecture because it's totally related to what we are talking about. It's just the reverse of what we want to do, right? Okay, so we have some agreements here. So this time we use set var, okay? So this time we use set var, but instead of setting x to something, we set this thing to the value that we want to represent. Is this the same concept? No, IEEE is the name of a huge organization of electrical engineers. So they establish standards for a lot of things. So the double precision floating point number is only one of the standards published by the IEEE, but there are many, many other IEEE standards, including the standard for C and C++. There's an IEEE standard for C and C++. Okay, so getting back to GDB, which is what we are seeing here. So let's go ahead and set this to what we want to represent, which is 61.375, okay? Press the enter key. Hey, not a problem here, okay? But now we want to look at the binary representation and see whether we are getting back, what we are expecting, okay? So let's work out what we should be expecting first, okay? So let's go back to this example here. And I need to get to the right point, which is here. Okay. So now we want to look at the bit pattern and find out, what is the actual bit pattern to represent 61.375. So we can say double representation of 61.375. Okay. And the first thing, the easiest part of this would be the sign bit, right? So the sign bit, okay, this is where I'm typing. So the sign bit is going to be a 0 because the value that we want to represent is not negative. And now we want to say, what about E? What about the biased exponent? Well, let's not worry about the biased exponent. Let's go back to the non-biased exponent E2 first. So we figure out that E2 is 5, okay? And, oops, okay, 5. So E, which is the biased version of 5, is just 5 plus 1023. So this is just E2, whoops, E2 plus 1023, which is 5 plus 1023, which is 1028. Okay, so are we doing okay so far, with these concepts? Daniel typed, is the double type 64-bit by standard everywhere? Yes. So whenever you mention double, it is 64-bit. Can anyone guess how many bits is one single? 32 bits. If a double is 64 bits, a single is 32 bit. And there is a quad also, okay, which is 128 bits. Cool. All right. But we want to look at E as a base 2 number, okay? So E as a base 2 number is 1024 plus 4 in base 10. So that means it is 1, let's see. Nope, there's no quarter precision or half. I don't think there's a half precision. I only know of single precision. Okay, so let's work this out, okay, because I need to look at all the, okay, let's just fill this in with 10 zeros first. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, base 2. Okay, now we go back, to backfill which one should be a 1. Okay, so I'm just going to do the counting over here. This is 1, 2, and then the 4. So that means this needs to be a 1 over here. All right, so we got E already expressed as a base 2. Now we need to look at F, okay, which is the fractional part of the mantissa. That's the easiest part ever. Oh, okay, so there is a half precision. Single precision, double precision, quad, and octuple precision. Wow. Very good, Aiden. All right, so getting back to the task at hand. This is the mantissa. This entire thing is the mantissa, but only the fractional part is represented, meaning that only this portion is represented. So that means I need to specify F, kind of focus here down to this part here. So F as a base 2 number is going to be 1, 1, 1, 0, 1, 0, 1, 1, and a whole bunch of zeros after that, okay? Like that in base 2. So the idea is F, the fractional part of the mantissa, should have 52 bits, okay? So these dots here are basically a whole bunch of zeros in order to end up with 52 digits altogether, okay? So with all of this in mind, okay, so now we look at this and go like, what would this 64-bit number look like, okay? So the double is going to be, first of all, it starts with a sign bit. Then it has the E, the base 2 version of the biased exponent, which is what we see up here, okay? So now we have one, okay, I'm just going to copy and paste because I can't count zeros. Okay, so we got copy and paste. There we go. And then we have the fractional part of the mantissa, which is just this portion. So I'm just going to copy a whole bunch, not all the zeros because we can deal with the zeros easily enough. So we have this bunch over here and a whole bunch of more zeros down here. Okay. So just like before, we'll go ahead and reorganize things a little bit. So we take out all the original spaces. Okay. And then we start to divide it into chunks of 4, starting from the left-hand side. Okay, this is important. So we got 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, and then the rest are all zeros. So now we look at this, and then okay, let me change the format. Okay, doesn't want to do it that way. Okay, I think, I'm trying to get it to put it into a table or pre-formatted style, and it doesn't want to do it. There we go. Okay, now we can do it. All right, so this is a 4 in hexadecimal. This is a 0 in hexadecimal. This is another 4. This is an E in hexadecimal. And this is a B in hexadecimal followed by a whole bunch of zeros. So what we really need to do is to say, well, we only want to look at the first 5 digits, the most significant 5 digits of the base 16 representation of this bit pattern. So now we go back to the debugger, and this time we do exactly the opposite, which is printing in hexadecimal what X has. Okay, and that turns out to be 404EB. Okay, 404EB, and then a whole bunch of zeros after that. So in other words, I just reversed the process, starting with a value that I want to represent, and then we get to the binary representation inside the double. So I'm hoping this particular experiment, this particular exercise, is helping you to understand, what a double really is and how to do the conversion, at least for easy values. Okay, 61.375 is an easy value because we can easily break it down to you know just powers of 2, limited numbers of powers of 2. Aiden has a very good question. How do we represent 0? As it turns out, there are a lot of exceptions to the rule. Okay, so if you look at the double, okay, there really is no way to represent true 0 because we know this part is either a 1 or a -1. Okay, this portion here, okay, I can't really select it, but this portion inside the big parentheses is always going to be at least 1, right? If you have all of these bits here, all the fractional bits being zeros, we still end up with a 1 over here. And this part here, 2 to the power of e minus blah, 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 is always non-zero also because it's always a power of 2, which is not going to be 0. So that means there's no true way to represent the value of 0. So IEEE says, well, guess what? If every single bit, in the entire 64-bit number are zeros, we'll call that representing true 0, okay? But if you use this equation, it will be representing a very small value. But IEEE just says, nope, 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 this is a special bit pattern. If you see this bit pattern, it really means 0, 0, okay? So along with 0, there are other interesting bit patterns too. I think there's one for positive infinity, one for negative infinity, one for positive not a number, and then one for a negative not a number. So there are many other special bit patterns where they are not really representing a specific value, but the computer, whatever is interpreting the bit pattern, will know what to do with it. Well, when you only have 64 bits, you only got so many choices of having to represent certain things that would make sense or is necessary in math functions, and that's why we have those kind of special patterns to represent not values but more like conditions. Okay, all right. So we are running out of time by 6 minutes. I will not charge you for the extra 6 minutes, by the way. But are there any questions before I stop today's live stream? There's a lot of stuff in today's lecture. I'm seldom called that, especially when it comes to grading. Oops, I shouldn't say that. Should not have said that before the end of the semester. Just roll back, delete that, undo, Control Z. But seriously. Okay, so seriously, are there any questions about today's lecture? If you don't get all the concepts right away, just watch the video again. But this time you might want to take notes and also pause it. Just pause at every single major concept or major step in the derivation, and make sure you make the connections between all the steps. Yeah, we can have more practice next Thursday because we'll have Tuesday for exam one. So next Thursday we can have more practice. And you guys can even think of examples too. Oh, okay, thank you, Aiden. That is how we represent positive infinity. So negative infinity would have the leading 0. The lab is not due on Tuesday. The lab is due on next Thursday because it doesn't make sense to make it due on Tuesday because we don't have any lecture on Tuesday. So it only makes sense to make it due on next Thursday so that the concept that you utilize in the lab would hopefully help you with the content of the lecture next time. Yeah, well, that's the only way to do it, Tom, because if you're only given a limited number of bits, then you can only use a particular bit pattern to represent whatever you need to represent. So that's kind of the what the deal is. Well, it's not really ironic, it really is a matter of modern day computers or digital computers. So yes, we have terabytes and terabytes of stuff, right? But it is still finite, which means values that we need to represent must be somewhat representable to an acceptable level using a finite number of zeros and ones. And as a result, we just have to be practical enough to have enough precision. In other words, when you specify pi, okay, the mathematical pi, it's an irrational number. Okay, it will take up an infinite number of digits in any base in order to represent it. All right, but do we actually need that kind of precision? The answer is no, not in most cases. So we would just say, okay, if we approximate the actual value of pi using a double, okay, which basically approximately has 52 bits dedicated to the precision of the number, because the exponent doesn't affect the precision, only the fractional part of the mantissa changes or affects the precision. So that means we just say, well, with 52 bits, I think we have enough precision to specify an irrational number for all practical purposes. And well, most of the time it is. All right, cool. So Nan has just one extra one in the Mantissa. Very good. Yep, not a number. Not a number is represented by a bit pattern. To be very specific, okay, Aiden, not a number is represented by a bit pattern. All right, so I am going to sign off if there are no additional questions and come back in about 10 minutes if there are any questions about the lab. And it doesn't hurt to get started on the lab, okay, because you can basically just continue to work on it for the entire week. So I strongly encourage people to start it and just kind of hang on to it. Don't submit, okay? You keep working on it until next Thursday, right before class. Yes, we just talked about it in today's lecture. The road calling thing, the road taking thing is IEEE in all lowercase. Yep, so you guys all have a good weekend. If you don't, contact me, and don't forget to study for exam one. And if I don't post the key to the to the other variation of the test by the end of tomorrow, just kind of give me a nudge. And the code of tonight's lab is indeed double. Yeah, I know I'm not too creative. All right, have a nice weekend, everybody. And I'm gonna go get something to eat, but I'll be back in about 10 minutes just in case anyone has any question. All right, cool. I